if you have, I'm Rebecca, by the way, if you don't know me. And if you have any questions, feel free to ask me either in class, after class, email me, come by my office. I sent out an email this morning that has my office number in it. Also today I am going to ask y'all to turn something in. It's not going to be graded, but I do want to go ahead and collect it. And so if you're here, just write your name on a piece of paper to turn in. And for those of you who are online, when you get done today, just email to rrune2@lsu.edu. And that's just some exercises that we're going to do in class today. All right, so before we get started, my handwriting it might be a little bit better now that I've put this down. Any questions that anybody has on any topics before we get started? All right. Other piece of information that you might want to know about. There is homework now available, homework 4. The due date is a Sunday. That's my fault. I've messed that up, but I just figured rather than change it, I'll just leave it where it is. It gives you a little bit more than a week to do it. I think the next homework will be due, I can't remember, but about a week after that. So you have a little less time than usual to work on it, but you still have plenty of time. And if you have questions on it, again, I'm available to answer those. I'm not sure when Dr. Trahan will be back, but do feel free to ask me questions. All right, today's topic is about a serial adder. In Digital Logic 1 in 2741, you learned about a ripple adder and a look-ahead carry adder. And now we're going to look at how to do an adder using sequential circuits, so using flip-flops. And to me, this makes a lot more sense when we get to the end and we actually look at an example and we say, okay, well, how would this actually work? Because when I started with it, I said, well, how is this really different from what we did before with the ripple carry adder, because it kind of sounds the same, and you'll see that the implementation of it is different. So a serial adder receives input bits one at a time and produces some bits one at a time. So when we say that, when we're adding together, it says inputs A n minus 1 to A0, we have an n bit number. So our first number A would be something like 1 0 1 0 1 0 1 1, and B would be 0 0 1 0 1 0 1 0, something like that. And then you come up with the sum, and you know how to add binary numbers. So the sum would be 1 plus 1 is 0, carry the 1 1 0, carry the 1. Any of you who've had me as an SI in circuits know that I can't add, I can't subtract, I can't multiply. So if I make a mistake, just say, yeah, 1 plus 1 is not 1. That is my most frequent mistake on tests is 1 times 0 is 1. On almost every test I ever take, somewhere on there, I will multiply 1 and 0 and get 1. Let's see. But in binary, 1 plus 1 is 0. So at least there's that. Okay. So I just added that in a serial sort of way, just one bit at a time. So I did one bit and then did the next one. And so far that kind of seems a lot like our ripple carry adder. And so this example that we had here, this one had 8 bits. So this would be A0 and this would be A7. And our sum, this would be S0 and S7. But you do have to keep track of the carry. So it really does have to be sequential. I can't just add the 4th bits together and then the 6 bits together, because the carry is important. And when we do this, we're going to use a shift register. So what is a shift register? Yeah, so on the clock edge, it shifts everything by, well, either right or left and however many places, but it shifts it. And we're going to use those. And you talked about parallel and serial. And if you look, these shift registers, they're going to have a parallel load. So you can load all of A all at once and all of B all at once. And then it'll shift. So it'll have a parallel load and then also a serial shift. So you'll have those. Then you'll have this adder finite state machine, and this is our new thing that we're going to be learning today. And then you're going to have a shift register that's going to store the sum. So that's what we're going to be looking at. And at any point, if you have any questions, please do ask. Okay, so we're going to start by coming up with a Mealy type state diagram for a serial adder. And that's going to describe what goes on inside this box. So this is what we're trying to figure out how to do right here, and we're going to do it in a Mealy sort of way. And Mealy means, now those of you on Zoom can't tell, but everybody in here, they're fighting to give the answer. They're just. All right, so you won the contest, yes, and the output does depend on the input. So, and does a Mealy or a Moore machine tend to have more states? Moore tends to have more states, so the Mealy has fewer states. So, what we are expecting to see here, let's see, what do I want to do? Okay, so our idea is going to be as follows, that our states are going to be whether or not you've received a carry or not. Okay, so why does that matter? So let's say I have just AI, I'm at the ith bit, AI and BI. So my sum is going to depend on AI and BI, and also whether or not I received a carry. So whether or not I received a carry, how many states is that? Received a carry, didn't receive a carry. Yeah, just 2 states. So I'm going to have 2 states. One of them is going to be received a carry, and one of them is not. And then my inputs, I have 2 bits that are my inputs. I'm going to have an AI, something from A and something from B. And so I have 4 different possible inputs that I can have. I can have 0, 0, 0, 1, 1, 0, and 1, 1. And then my output depends on my input, and it will be the sum of the 2 bits that I have and whether or not I had a carry or not. So if I call this state that, I call this one G. Nope. This one is, to have it in the same order as what I'm going to have below, I'm going to change this. Did not receive carry, and then did receive carry. And then this one will be G, and this one will be H. And that's just to match the notes that are coming up. So if I did not receive a carry, and I have as an input 0, 0. So I got a 0 from A and a 0 from B. what's my output going to be? What's my sum? Yeah, so 0 plus no carry is 0. So that would be my output. So you need to figure out right now, and this is on the piece of paper that you have, and then you can copy it into your notes if you want to. You want to figure out the other 7 arrows that go on this. So I have, and you can use the same arrow for more than one input if it has the same result if you want to. But we have 4 different possible inputs for did not receive a carry and 4 different possible inputs for did receive a carry. So I want you to put those arrows on. And for those of you who are watching on Zoom, do this, and then at the end you're going to email it to me. I didn't explicitly say, but the reason why my arrow curved back to G is because when I added 0 plus 0, I didn't have a carry, so I returned back to the state of not having a carry. If I added 2 things that did have a carry, I'd have to go to the state that had a carry. Is this about typical for how many people come? Okay, didn't think so. All right, so let's check that. And like I said, this is not graded, so if you want to change, it doesn't matter if you change what you turn into me or not. It's actually kind of useful for me if you don't change it, if you have, if it has mistakes, but if you want to change it because you're like me and you want it to be perfect, that's fine. So if we are in the state of no carry, then we are going to go back to the state of no carry if we receive 2 zeros or a 0 and a 1, because that would just give me either a state of 0 or 1 without a carry. And so 0, 0, 0, 1, 1, 0 all return back to the state of no carry, which is G. And then, but if you have a 1 and a 1, 1 plus 1 is 0, carry the 1. And so that turns you over to the state that has a carry. So the state H is where your carry in equals 1. The output is the sum, so 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 right here is 0, carry the 1. And then if you're in the state with a carry, so like right here, if I got a 0 and I got a 1, 0 plus 1 is 1, but I had a carry in, so I add that in as well. That gets me a 0, carry the 1. So my output is my sum output, my sum bit is 0, but I stay in the state of having a carry in of 1. So I'm going to make sure everybody has a chance to get this down if you're going to write it down. Does it make sense, or how did y'all do with it coming up with the diagram? Was it pretty close? Okay, so the next thing that we're going to do is we're going to make a state table for this. So it'll be pretty straightforward. I'll bring that back if I think I'm not going to have y'all do the state table on your own. We're going to do it. We're just going to look at it together. Okay, so we've got the state diagram up there, and then here we have the state table. So the state table has our output is just a single bit. It's our sum bit, and that's just going to be 0 or 1. And our next state is just whether we are in the carry n equals 0 or the carry n equals 1. So this state table is just a way to kind of summarize the results that we have in the state diagram. So there's nothing new about this, except that it's, you know, kind of different looking from most of ours in that we only have 2 states, but we have 4 possible different inputs. So you know, probably haven't seen one like that yet. And then from here, we can get the state assigned table. If we have 2 states, how many flip-flops do we need? 2 states. Just 1 flip-flop. We only need 1 flip-flop because 2 to the 1 is 2. So we just need 1 flip-flop, and we can assign these. We could assign G to be 0 and H to be 1. So then if we change this to a state assigned table, then we can let our flip-flop value will be Y. So Y is going to be our next state. And we just need the 1 variable for that because we just have the 2 states. And our present state is going to be lowercase y. And our output is going to be S. Now, you no idea what I was going to say. I'm sure it's fascinating. Y, capital Y, S. Yeah, no, don't know. So all this was the only thing that I did here. Well, I didn't do it, but is the G's are 0s and the H's are 1s. And then once you have that, you can then come up with the equations if you needed to. So let's do that for one of these only. Let's do capital Y, and Y depends on, let me do this in a better place. So Y depends on my 2 inputs, which are A and B, and also my present state. So Y depends on AB and my present state. And AB can be 0, 0, 0, 1, 1, 1, 1, 0, and my present state can be 0 or 1. And I see that when my present state is 1, I have 1s in everything but 0, 0. And when my present state is 0, I only have a 1 in 1, 1. And the best way to get this is with this grouping, and that is AB or BY or AY. I lied. I said I was only going to do one. I am also going to do my output because it's not that hard. So for my output, I have ones, whoops, 1, 1, 1, 0. I have ones for 0, 1, and 1, 0, and also 0, 0, and 1, 1. Right. Is that right? Yep. Top row. Like that? Yes. And then that's what I was expecting because I knew something was wrong because I knew what the answer was. And this is the characteristic pattern for something, then you'll see what it is. So you look at it and you say, oh no, that's terrible. There's no, I mean, it's the worst possible thing. And then I get not A, not B, Y, or not A, B, not Y, or A, B, Y, or A, not B, not Y. Now, you'll notice if I look at these and I think of the nots as zeros and the uncomplemented as ones, how many ones would I have? How many uncomplimented ones do I have in each of these that I underlined? I have one uncomplimented one in each of those, and I have 3 uncomplimented ones in that one. You'll notice that that's equal to an odd number of ones. Each of these has an odd number of ones. This is the exclusive OR. This is the exclusive OR of 3 things. This is A, exclusive OR B, exclusive OR Y. And this kind of checkerboard pattern is your clue that that was going to be an exclusive OR. So looking at those, you can see that your next state and output equations are as given right here. And you probably remember, of course, that when you learned about adders, that those were in fact the equations for the carry bit and the sum bit. You probably said, oh yeah, I recognize that we did that in 2741. Those are the equations. That is a full adder. And so that's what we get. Okay, so not surprising that when we add, we get something equivalent to a full adder. Now, if we do more, we're going to have more states. And the reason we're going to have more states is because our sum has to depend only on the state that we're in. But if you think about it, when we compute the sum depends on both of the bits that we get and whether or not we had a carry. And so I want y'all to look at this state diagram, and as soon as someone feels like they can explain it, I would love to get someone to explain it. This could be someone on Zoom or someone here. And I know it's going to be hard for me to pick the person who's going to want to volunteer to do this, but I'll, But don't be afraid. Don't think that you'll, don't be afraid to take the glory. So look at it, see if you can figure out what's going on. And I'll give you a hint. G and H have the same meaning that they had in our Mealy machine. And if you remember, G stood for the carry n equals 0, and H stands for carry n equals 1. Okay?
So the top left one and the top right one are what you said already, and then the bottom left one is whenever you have the output is equal to 1, so whenever you add just a single digit to it from the G, and the bottom right is when you have a carry in and the output is 1, so whenever you get the top right and add 1, and there's a lot of other ways you can do it, but that's two main ones.
Yeah, yeah. So what this is saying is we have the sum is depends on the state that. So we'll take an example. Like let's say that I had. Let's just do some numbers. Okay, so I have 0 plus 1 is 1 with no carry. So that means that I am in state G1 right now. My sum is 1, and I have no carry. So, got that. Now, I'm in this state, and I am adding together a 1 and a 1. So if I look at what happens when I add together a 1 and a 1, I know what I get. I get a 0 carry the 1. And sure enough, if I look at where that brings me to a state where my sum bit is 0, and I've moved to H now. H means my carry bit is 1. So H carry is 1. G carry is 0. Okay, so now I'm in state H0, and I've got a 0 and a 1. Well, I add together the 0 and a 1, and I get a 1, but I had a carry, so a 1, so that add the 1 to that, and that gets me a 0 carry the 1. So that should bring me back to state H0, which is my sum is 0 and I have a carry, and sure enough, a 0, 1 does bring me back here. Let's see what happens if my next one was a 1, 1. So 1 plus 1 is 1, but I had a carry. So that's 1 carry the 1. So I should have, my sum bit should be 1, and I should still be in H because I have a carry. All right, so how many flip-flops do we need for this one? And we need 2 flip-flops. And so this is just translating our state diagram to a state table. These are Dr. Tron's PowerPoints, so these are all online, so don't feel like you have to copy them all down right here. And it's exactly what, it's just transferring from one to another. And then the present state, they're defined 0, 0, 0, 1, 1, 0, 1, 1. You can define them however you want. There's no real advantage that I know of doing it one way over the other. So the biggest difference is that when you do if you come up with your equations, what you would get is you get y1 is A exclusive or B exclusive or y2. That's capital Y1. And capital Y2 is AB plus AY2 plus BY2. And S is Y1. So that is similar to what we had here, except here we only had one flip-flop. We only had Y was our flip-flop. Here we have two flip-flops, Y2 and Y1, and the sum bit is what's going through the other flip-flop. So we have Y2 is being used to compute our next state, and our sum bit is going through the other one. So which one is going to of the Mealy and the Moore, which one would be behind by one clock cycle compared to the other? Well, you can see it here. So when we look at the circuit, compared to, did we have a circuit for the other one? We did we? I'll draw it here. Yes, I need to think about this. So I'm looking at the notes here. So this is, we have resulting circuit is the same as before. Except you pass the sum through a flip-flop, delaying it by one clock cycle compared to Mealy. And I need to think about that a little bit and make sure I understand where the delay is coming from, because to me it looks like you have to wait a clock cycle to get the carry anyway. But I'll think about that. Okay, so now for the fun part, and that's the Verilog. Let's see, is there anything else I want y'all to write on that paper? Okay, so spend like 2 or 3 minutes on this paper that you're going to give to me, and in your own words, I want you to say how, just like not in any kind of detail, how does a serial adder work? And I don't care if you do Mealy or Moore or both, just what's the basic idea between how does a serial adder work? What's the basic idea behind it? No details, just assume you're explaining to somebody who already has any kind of knowledge you need them to have. And I see some of you are looking at this slide, and that would be fine. You can also be thinking about the, if you wanted to use a state diagram to describe it, that would be another way to think about it. Oh, I didn't get much of a state diagram there. Oh well. Okay, so it does not have to be a perfect description. So now I want to talk about how this Verilog works. You have a module that's just for the shift register. And the way the module works, you'll have however many bits is your parameter. So this is 8 bits. I'm just demoing with 4 to save time. You have an input, and your input, that would be your parallel load. So your input here is R. So that would be if I wanted to load a number. You also have an input L, and what is L? L is that input is telling you whether or not you're going to load or not. And so if L is 1, you load, otherwise you shift. So if L equals 1, load, otherwise shift. You also have E. E is enable. So if it's not enabled, you don't do anything. You have W. W is the input that you put in to the one that you have shifted out of, and it doesn't have something else to shift into it. And you have the clock. And so if we look inside this for loop, N is our parameter, K goes from our parameter -1 as long as it is greater than 0. So if N is 4, we would go from 3 to 1. And we are transferring, the order here is weird, but what it's doing is it's taking the value from 3 and sending it to 2, from 2 to 1, from 1 to 0, and then this external value W is going into 3. So that's how the shift register is working. You can either load, you load everything parallel, or you shift to the right. And are we doing anything with... No, we're not. We're not doing anything with the thing we're shifting out, because these are the numbers we're going to be adding up. And so once we add this number, once we add the 0-bit number, we're done with it. So we're going to be getting rid of it. So we're going to have our numbers that we're adding together. So I'll have my numbers. Let's say I've got 0, 1, 0, 1, 0, 1, 1. I'll go ahead and do 8-bit numbers. 1, 0, 1, 0, 1, 1, 1, 0. Okay, so here is the actual adder part. I have my inputs are going to be A and B, and that's these 8-bit numbers. I have reset, so that's if I want to start over. I have this wire, that's my sum. I have a count, so I'm going to keep track of how many times I've added. And then I've got my states and my sum bit, that's S, Y, and Y. And I've got these other wires, that's for my next state, because it's a finite state machine. I'll have my next state and then my current state. This wire called run is telling me, do I need to keep going, or am I done adding? And then I have my parameters, G and H. G is the parameter saying no carry, and H is the parameter saying carry equals 1. And then I set up my shift registers, and my shift register, my first one, has A, so let's take a look at the order here. This was R, that's the value to load. L, am I loading or not? E, am I enabled? W, what am I bringing in on the end? Clock, and Q is my entire output. Q is what are these values when I'm done. So Q3, Q2, Q1, and Q0. So when I look at how I'm instantiating this here, A, that's the number I'm loading. Reset, that's telling me, remember that was equivalent to L. That's saying, is it time for me to load or not? 1, binary 1, that was, am I enabled? So I'm saying, yes, I'm enabled. 1 binary 0, that's saying the number I'm going to shift in at the end is going to be 0. So once I've shifted, I'm not replacing it with more numbers. Clock, and then QA and QB. And then I also have a shift register to hold my sum. So here's how this works. I'm going to add together the numbers in the 0th position. So this is 0, 1, 2, 3, 4, 5, 6, 7. And I'm going to add them together based on what we learned about our machine before. And so we'll have the state. The state will say, am I in a carry state or not? And, well, actually, when I first start, the first thing I'm going to do is I'm going to say, the first thing I'll do is I'll reset. And when I reset, I set myself into a not carry state right here. So that's the first thing that I do. So the first thing is reset. You set yourself into a not carry state. Okay. Then you add together these numbers, and then in your sum is initialized to all zeros. So that is right here. You see that you're loading it with all zeros. Now you're going to shift everything. And to A and B, you're going to shift zeros in on this end. And to your sum, you're going to shift in what you got here. So everything moves to the right one space. This 0 goes here. And this is going to shift to the right. And I'm going to do that just by saying these are now gone. And I'm adding a 0 on this end. So this is now my 0 bit, 1 bit, 2, 3, 4. Then I go again. And when I do this, to check to see whether I run again, I have this value that is count. I set count to be equal to 8. I want 8. See, when I reset, I set count equal to 8. I'm going to subtract 1 from count each time. When I get down to 0, I'll say I'm done. How do I do that? I put that in my run variable, and if you remember, run here was the enable. And so if run is 1, it's enabled. If run is 0, it's not enabled. This is cool. I did not know this until I looked at this. So run equals or count. Or count. What this is the or of all of the digits in count. And so if count, remember count started at 8, so count started at 1, 0, 0, 0, and then I subtract 1 from it each time, 0, 1, 1, 1, and then 0, 1, 1, 0. So if you OR all the digits, you're going to get a 1 every time because you'll have at least one 1 in there until you get down to 0. So I had not ever seen that before, so I thought that was cool. It's just a new thing for me. Okay, so then I shift, and then next time through, this is now the 0th bit. I add these. I get 1, 1 is 0, so that's my next bit that I shift into the sum. And I got a carry, so that means I'm going to be in the carry state. And then I'll add together the next ones. I get that, and so each time I'm shifting my A's and B's to get the last digit out, and I'm taking my answer and I'm shifting it into my sum. I can't tell if that's making sense. I can't tell if y'all are bored or sleepy or making sense or not making sense. You got 1 minute to tell me. So I add 1 and 1 and I get 0. I put that into my sum. Carry the 1, 1 and 1 I get 0. Put that into the sum. 1 and 1 I get 0. I put that into the sum. That was boring. I'm probably adding wrong. But it's just regular adding. It's just you're using the shifter to do it. All right. That's all I have to say about that. If you have any questions, feel free to email me, or email me and we can or set up office hours and I can answer any questions in office hours. All right. Thank you for coming. Those of you who came both online and in person.